Welcome to the Deep Dive, where we take complex, high-stakes information and boil it down to the essential facts you need to be well-informed. Today, we're stepping into a really high-risk environment. We're looking at an extreme form of engineering safety, the rules for maintaining massive tires and rims on heavy mining equipment.
And when we say massive, you really have to picture it. We're talking about tires that stand taller than a person. These are for haul trucks that carry hundreds of tons of rock. Our focus today is specifically on any wheel assembly that's 24 inches or bigger. The scale is just, well, it's overwhelming.
And I imagine when you have that much size and that much contained pressure, the way it fails is completely different. It's not just an inconvenience, it becomes a lethal hazard.
Instantly lethal.
So our source for this is a fantastic piece of regulatory thinking. It's the Penhouse Group's safety standard, RSKP&A GLB STD 26, and it focuses purely on these giant assemblies.
It's a real window into the sheer explosive force that has to be managed every single day in these places. It dictates everything from how you select a component right up to its final disposal.
So our mission for you, the listener, is to really get what makes these massive tires so uniquely dangerous, the hidden physics of it all, and what engineering controls are absolutely non-negotiable to manage them. We're going to find out why the type of lubricant you use matters just as much as, say, the anchor chains holding it down.
Okay, so to start, let's lay the foundation for why these extreme rules even exist. It's all about comprehensive risk mitigation. This standard is compulsory for everyone, employees, contractors, even visitors on a Penhouse site. And the fact it only covers assemblies 24 inches and up tells you something.
Right, that's the threshold. That's where the risk shifts from serious to life and death.
Exactly.
It's also interesting what this standard doesn't cover. It helps you see how focused it is. It specifically excludes operating the equipment or the risks of lifting it for maintenance.
Yeah, those are covered by separate standards. This one is surgical. It is purely about the wheel assembly itself.
And that focus lets them get incredibly granular with the risk control.
It does. The core philosophy, which is in section 4.1, is that you have to maintain a detailed risk register for the entire life cycle of the wheel. This isn't just some maintenance checklist.
The life cycle approach is fascinating. They have to think about hazards long before the tire is even bolted on. So risk from selection, storage, fitting, maintenance, all the way to disposal.
Right. Every single stage has its own identified hazards and its own required controls. Even just storing these things is a safety concern. They're so large they could fall and crush someone. It's risk management on a massive scale.
And this is where the accountability really kicks in, with the requirement for a job safety analysis, or a JSA. Now, it makes sense that you'd need one for a new task or a non-routine job, but the standard also says you need a JSA if the environmental conditions change. Why is that?
That is a brilliant piece of regulatory insight. I mean, why would rain matter when you're just changing a bolt? It matters because heavy rain, strong winds, even high humidity. It can compromise your control over the situation. Rain can make the ground unstable for jacks or make your tools slippery.
Ah, okay. So it's not about the component failing because of the weather. It's about the environment causing a human error, a slip-up that puts a worker in the danger zone at exactly the wrong moment.
Precisely. Any deviation from the norm means you have to stop and reevaluate if your standard procedure is still safe.
Okay, let's move into what seems like the most critical part, the pre-work and depressurization. This is where the zero-tolerance rules really show up.
Yes, because this is where that contained energy is released either by design or, by accident.
Let's start with the absolute prohibition against heat.
It's crystal clear in section 4.2.1. No welding, no cutting, no applying heat from any source, not even a small torch to loosen a nut, is allowed on any assembly with an inflated tire. It's strictly prohibited.
I get the danger, but why is it an absolute ban? These parts are made of high-strength steel. Shouldn't they handle a little heat?
It's not about melting. It's about thermal shock. You're applying localized, intense heat to steel that's already under massive tensile stress from the air pressure. That can cause a catastrophic brittle fracture. Basically, you're turning a structural component into a high-velocity shrapnel bomb.
That's a powerful image. And the standard says if you absolutely must use heat, maybe on a seized component, you need a JSA, and the tire must be completely, totally deflated.
Zero inflation. And on that note, there's no repairing these things, no welding patches on the rim. If it's damaged, you replace it. You don't patch something that's holding back that much lethal force.
Okay, so how do you get the pressure out safely? The standard actually details two different deflation requirements depending on the type of tire.
It does, and this distinction is crucial. For tires with split rims, where the rim is multiple pieces held together by the pressure, they must be deflated completely, to zero. Any pressure at all could launch a piece of that rim.
But for the other types, it says they can be deflated to a pressure no greater than 5 CI. Why the difference? Why leave any pressure in at all?
It's likely about the design. On a monoblock rim or one with a single heavy lock ring, that tiny bit of pressure, and 5 psi is almost nothing, it keeps the component seated against the seals. It prevents dirt from getting in while still being safe enough to work on.
So that tiny 5 psi is the absolute maximum safety threshold. It's amazing that the margin is that small. And for dual assembly, like on a haul truck, you have to deflate both tires, even if you're only working on one.
You never want differential pressure on a shared hub. And there's a small detail in there I like. They recommend noise mufflers during deflation. These things are incredibly loud when they let go.
So after deflation, we're into ongoing maintenance and integrity. Section 4.2.1 requires regular visual inspections. What are they looking for?
They're looking for the obvious stuff like pressure and tread wear, but also for the subtle signs of a coming failure. Things like tire separation, signs of fatigue, damage to the valve. If a fault's found, it's marked and reported immediately.
And this goes way beyond just a visual check. There's a requirement for some serious structural testing, right? Following specific Australian standards.
That's right. Section 4.2.3.2 says all components have to be tested according to Australian standard AS 4457.1. And that standard is specifically about finding the silent killers. Metal fatigue, stress fractures, things you just can't see.
So that standard number is code for we're hunting for micro failures. And that means a complete teardown, I assume.
Absolutely. The tires have to come completely off the rim for this inspection. You inspect both internal and external surfaces. It often involves non-destructive testing, NDT, like ultrasound or magnetic particle inspection.
That level of testing, plus the service records, must give them a real sense of when a component is nearing the end of its life so they can replace it before it fails.
That's the whole point, is moving from reactive maintenance to proactive retirement of parts.
Okay, let's talk about getting a tire ready for service. The surge rules are pretty straightforward. Keep them on level ground so they can't fall over. But the marking requirements are incredibly detailed.
Before any rim or tire goes into service, it has to be permanently marked. It gets a unique ID number, its type, its size, and the date of manufacture. And that ID has to be visible even after it's fitted and inflated.
So that ID is like the component's social security number. It tracks every single thing that happens to it through its entire life.
Exactly. It's all about accountability.
And then the actual assembly. We talked about heat being bad, so I'm guessing you can't just use regular old grease to mount these things.
That is correct. The mounting lubricant has to be non-flammable and non-hydrocarbon.
Why is that? What's wrong with normal grease?
It's the friction. The friction between the tire and the rim during fitting, or even just flexing during normal use, can generate a ton of heat. If you use a hydrocarbon lubricant, you've just introduced a significant fire risk, an ignition source.
Wow. And they also mandate rust inhibitors and lock ring retainers. It's all these tiny details that add up.
They all prevent a future failure. Rust can mess up the fit of the lock ring, and if that ring shifts even a tiny bit under pressure, you're in a very dangerous situation.
Okay, let's get to it. The single highest risk moment in this entire process, inflation. This is where a hidden defect becomes an explosion.
It is. A single 57-inch rim assembly, which you'd find on the biggest trucks, can hold enough compressed air that if it fails, the force is enough to throw a 200-pound piece of steel a quarter of a mile. It's like a rifle shot. It is a localized industrial bomb.
So given that unbelievable amount of potential violence, what are the mandatory engineering controls to protect the worker?
Section 4.2.4.3 lays out 4 non-negotiable safety features for the remote inflation system. It's all designed to enforce distance and control.
Okay, walk us through them one by one.
First, a mandatory 5-meter exclusion zone. No one enters that zone while the tire is being inflated, period. Second, a remote airline valve. The on-off switch for the air has to be outside that 5-meter zone.
Distance and remote control. Got it. What are the other two?
The third is a remote dump valve. This lets the operator immediately release all the air without ever going into the zone. If something looks wrong, they can depressurize from a safe distance. And finally, the pressure gauge must be readable outside the exclusion zone. You need feedback without proximity.
That's a perfect system of layered controls. Distance, start, stop, and an emergency kill switch, all monitored from safety. But you still need physical restraint.
Oh, absolutely. All tires have to be inside an anchored cage guard or some other restraining device during inflation. And the key word there is anchored. That cage has to be able to absorb a catastrophic energy release.
What I found really fascinating was the rule about reinflation. You can't just top off a low tire.
No, you have to assume there's been structural damage. If a tire has been run on less than 80% of its cold inflation pressure, it cannot be reinflated until it's been fully inspected for damage. For duals, both have to come off and be inspected.
Why is running it just a little low so bad that it requires a full teardown?
Because when these huge tires run underinflated, the sidewalls flex way beyond their design limits. That flexing generates a massive amount of destructive heat, and it can cause the internal layers of the tire to literally pull apart. Reinflating that tire is like inflating a bomb.
You have to confirm its integrity first. And even before inflation starts, all the fasteners have to be torqued perfectly.
Absolutely critical. Tightened to the manufacturer's spec and alignment checked before and after torquing. Misaligned parts under that much pressure are a guaranteed failure point.
So that covers the pressure risks, but there are external hazards too. The standard requires mitigation for tire fires and explosions caused by the environment.
Right. This is about external ignition sources. For instance, they have to establish minimum heights for power lines based on the biggest equipment to prevent contact, which could cause an electrical fire and a tire explosion.
And lightning. A giant metal vehicle on huge rubber insulators.
Yeah, they have to have systems to detect lightning at a certain distance, which then prompts them to suspend operations. A direct lightning strike can ignite the rubber, leading to a massive fire, and then, boom, the tire fails explosively.
It's clear the tools for this job have to be just as rigorously maintained as the tires themselves.
Of course. The standard mandates monitoring and calibration for everything: pressure gauges, deflation valves, and especially torque wrenches. An inaccurate torque wrench could lead to fasteners being too loose or too tight. Either way, you've just undermined the entire safety system.
And finally, let's talk about the people, the human factor. Competency is obviously mandatory, but there's a specific higher requirement for the really critical integrity checks.
Yes. All personnel have to be trained and competent, but any non-destructive testing, the NDT we talked about for finding internal cracks, that can only be done by someone competent in accordance with international standard ISO 9712.
What does referencing a global standard like ISO 9712 tell us?
It means they're not just relying on their own internal training for this. ISO 9712 is the highest level global certification for NDT technicians. They are essentially outsourcing this life-critical assessment to globally certified specialists. The stakes are simply too high for anything less.
And to close that loop, the standard requires mandatory record keeping. It's not just about doing the work, it's about proving it was done correctly.
Every action creates a robust, auditable paper trail. Risk registers, inspection histories, training records, incident reports. It ensures maximum accountability and lets them learn from every single observation.
This has been an incredibly revealing deep dive. The sheer level of detail, from the chemical makeup of the lubricant to mandating globally certified inspectors, it just underscores the terrifying forces contained inside these assets. The engineering controls are a direct physical response to the physics of failure.
The force contained dictates the control required. That's really the lesson here. This standard is a textbook example of how to govern a high-risk system with absolutely zero tolerance for error.
So what does this all mean for you? We've just looked at the meticulous, extreme measures needed to maintain a single wheel on one truck. Now imagine scaling that across a huge mining site with hundreds of these vehicles operating 24/7. Considering the governance required for just a tire, what unseen regulatory complexities exist in the routine maintenance of other things we take for granted every day, from the expansion joints on a skyscraper to the deep-sea anchors of an oil platform? That's your thought to mull over until our next deep dive.